Once again, you're all welcome, as always. We've looked at Pareto optimality, Pareto efficiency. We're able to look at two situations where one is Pareto optimal and the other is not Pareto optimal. Okay. Now, we want to look at a very quick thing in the prisoner's dilemma called the zero-sum game. Okay. But you just want to learn what a zero-sum game is. It's a simple thing. What is a zero-sum game? The name is very clear. A zero-sum game is where one man's meat is another man's poison. It is where one player's gain is exactly the other player's loss. And there are games like that. In a chess game, when one loses, one has gained, one has won. In a poker, when one wins, one has lost. Football is not truly like that. Football, there can be draw. But for somebody, even a draw is a loss. And the other person, a draw is a win. It's about how one looks at it. So at the end of the day, there is a constant item that moves from one to the other. So one loses one and the other gains 1L. That is a zero-sum game. Okay. So the question we want to ask ourselves is that, is the prisoner's dilemma a zero-sum game? Now let me remind you of the prisoner's dilemma. The prisoner's dilemma is this situation where they both don't confess, they get 1 year jail sentence. They both confess, which is what they eventually chose. They both confess, and then they both get what? They get 6 years, 6 years. That was a conclusion in the zero-sum in the game. So now for this game to be a zero-sum game, one man's meat should be another man's poison. One man's loss should be another person's gain. Okay. So when I am losing, you are gaining. And I'm talking about that in every payoff, in every cell. So in every cell, one man's meat is another man's poison. So if one is getting +1, if Husseini, which is a red guy, is getting +1, then Pierre is getting -1. That's what it means. If Husseini is getting +15, then Pierre is getting -15. It's not 0-0. It's not 6-6. So tell me, is this game a zero-sum game or is not a zero-sum game? You can raise your hand and tell. Is this a zero-sum game or is not a zero-sum game? Let's make it quick. Okay, let's go to McLeod. So McLeod, what is it?
Hello, so it's not a zero-sum game because the cases where both of them are winning, not one losing and one gaining.
So this is not a zero-sum game. Now I'm going to show you some couple of things, then you tell me whether they are zero-sum games or they are not zero-sum games. So this is it. Okay, this is not a zero-sum game. One player's gain is not exactly the other player's loss. Okay. So that is it. I'll later give you some things and then you check. So anytime you're answering game theoretic question in the basic form, you remember I've taught you the basic form. These are some of the things you need to find. You should be able to identify the players in the storyline, the strategies, and the payoffs. That's the first thing. You need to be able to tell whether it's a simultaneous move game or it's a sequential move game. And please, for this one I taught you, all of them are simultaneous. Simultaneous move game, we use the matrices, the normal form to represent it. And since I didn't use any game theory, okay, everything is a simultaneous move game. Presenting the game in a normal form is an important skill you need to learn. You need to learn that. Does either player have a dominant strategy? We looked at that. We told you that there are ways where a player can have a dominant strategy. When one player makes a choice and sticks to that choice, irrespective of what the other player does, then we say that player has a dominant strategy. And when the other player also has a dominant strategy, then one of the equilibrium, the pure strategy Nash equilibrium, means that we have a dominant strategy Nash equilibrium. Under the pure strategy Nash equilibrium, we indicated that there are three ways to arrive at the pure strategy Nash equilibrium. There are three ways to get the pure strategy Nash equilibrium. Who can remember one of them? Who can remind us of one? There are three ways. There are three ways of arriving at the pure strategy Nash equilibrium. Who remembers the first? I've said it even right now. The first one is the dominant strategy approach. The dominant strategy approach means that if you have a dominant strategy and I have a dominant strategy, which means that if you decide to play the strategy A and I decide to play the strategy C, and it doesn't matter what I do, you will play that. And it doesn't matter what you do, I'll play that. Then you have a dominant strategy and I have dominant strategy. Then we can use that dominant strategy to arrive at the pure strategy Nash equilibrium. And that is known as the dominant strategy Nash equilibrium. Who can remind us of the second way that I mentioned can be used to arrive at the pure strategy Nash equilibrium? Michael Kamwa, do you remember the second way? Michael Kamwa. You can unmute yourself. Precious Do, do you remember the second way? Precious.
No, Doc.
Okay, Kajitan.
No, Doc.
Okay. Michael says no. Okay, so the second way we are going to look at it, and I mentioned it the other day, the second way is that we use something known as iterative elimination of strictly or weakly dominated strategy approach. And the third way is the best response approach. Okay, so that's what we're going to do. That's what we're going to do pretty soon. So get ready.